Okay, for 29, the angle of elevation from a person lying on the ground to a hot air balloon is 37 degrees. The balloon is at an altitude of 1,500 feet. To the nearest foot, find the direct distance from the person to the balloon. Okay, first I'm going to illustrate this with a figure or some kind of diagram. There's a person laying on the ground, and then I have he's looking up at a balloon, and that makes a 37-degree angle with the ground. That line of sight makes a 37-degree angle with the ground. It says the balloon is 1,500 feet high. So that's its altitude, which would be perpendicular to the ground. And I want to find the direct distance from the person to the balloon. So that is that direct line of sight distance, and that would be the hypotenuse here. Okay, I'm given the opposite side, and I'm looking for the hypotenuse, so that's going to be my unknown, and I'm going to use sine again. So the sine of 37 degrees is 1,500 divided by x. Okay, when I multiply both sides by x, I get x times the sine of 37 degrees equals 1,500, and now I can divide both sides by the sine of 37. Making sure you're in degree mode again. 2,492 feet. That's how far away the person is from the balloon. I'm sorry. On number 30, we're asked to find the length between M and N. And they're given as a diagram. One thing that's not shown here is that this is in fact a right angle. So we're going to be using trig to find this distance. So I'm going to look at these as two different triangles. I have the smaller triangle that will help me find this length because it is the adjacent side to this 50-degree angle. And then I can also look at the larger triangle where I can solve using this 25-degree angle for this length. And when I know both of those lengths, I can find the difference. So that's what I'm going to do. I'm going to set up two trig functions to find these two lengths. So I'm going to start with finding what I'm going to call distance M. And since my angle is 50 degrees, I have the opposite, and I'm looking for the adjacent leg. That's the tangent function. The tangent of the angle is opposite over adjacent. So the tangent of 50 degrees is 3,000 over M. Okay, I'm going to multiply both sides by M and then divide both sides by the tangent of 50. So M is equal to 3,000 divided by the tangent of 50, and that's going to be 2,517.2989. I'm going to keep several decimal places until I'm finished. Okay, now I'm going to work with the larger triangle and find the distance to N. Okay, looking for this distance, I have angle 25 degrees. I know the opposite. I'm looking for the adjacent, so I can use tangent again. Tangent of 25 degrees is equal to 3,000 over N. Okay, solving this equation the same way, I end up with N equals 3,000 divided by the tangent of 25. Which is about 6,433.5208 feet. So to find the length between M and N, I'm just going to subtract the two. 2517.2989 minus 6433.5208. I'm around to the nearest hundredth, 3,916.22. For 31, we're asked to find the probability that a point chosen randomly inside this 60 by 30 rectangle will fall in a shaded region. To find the probability that it lands in the shaded region, we're going to have to look at the area of the shaded region. Compared to the total area of the rectangle. The total area of the rectangle. So I'm going to call that a rectangle region 1. I'm going to call this other small rectangle region 2 and the triangle region 3. And in order to find the area of that shaded region, I'm going to take the whole area, the 60 by 30 rectangle, and subtract the other pieces that are not shaded. So I'm going to start with region 1, which is the big rectangle. The area of that is base times height, so that is 60 times 30, and that gives us 1,800 square meters. Region 2 is that smaller rectangle. It is 7.5 times 10, which is 75 square meters. And region 3, it is a triangle, so that's base times height over 2. In this case, we're not given our base, but we are given that it's a right triangle, and we know one leg and the hypotenuse. So using either Pythagorean triple or Pythagorean theorem, you can calculate that this bottom leg is 20 meters. So for my area formula, I have 20 times 15 divided by 2, which is 150 square meters. Okay, so now to find the area of the shaded region, I'm going to take the area of the large rectangle and subtract the other two pieces. And I'm left with 1,575 square meters. So now I have all of the information that I need in order to solve this probability. I need the initial area of the big rectangle, the area of the shaded region, and I can plug it in. 1,575 over a total of 1,800. If I reduce that fraction, I end up with 7/8, which is 87.5%. So if I pick any point randomly inside this large rectangle, there's an 87.5% chance it will land in a shaded region. So for number 32, we're going to do about the same thing to find this probability. We're asked to find the probability that a point chosen randomly inside the triangle will fall in the shaded region, and it gives us the diameter of the circle is 10, so that tells me the radius of the circle is 5 centimeters, and the side length of the equilateral triangle is 25 centimeters. Remember, equilateral means that they are all equal, all sides are equal. So in order to find the probability that it lands in a shaded region, we need the area of the shaded region, over the area of that total triangle. So in order to find the area of the shaded region, I need the area of the total triangle, and then I need to subtract the area of this little circle. One thing we need in order to find the area of the triangle is going to be this height. Okay, if I know the height is perpendicular, so I need to either use Pythagorean theorem or in this case special right triangles to find the height of this triangle. I know that this side is 25, and since this whole side is 25, half of it is 12.5. So I can use Pythagorean theorem or special right triangles to solve for this height. When I do that, I get a height that is 21.651. Now I have all the information I need to find the area of the triangle. Remember, it's base times height over 2. So it's 25 times 21.651 over 2. And that's approximately 270.633. I also need to find the area of the circle. That's always pi r squared. And the radius we found was 5. So that's 25 pi. So now I have the information to find the area of the shaded region. It is the total area of the triangle which is approximately 192.093. And when I come over here and put it in my probability formula, 192.093 over 270.633, that's approximately 0.7098, or about 71%. Okay, for number 33, we have a circle with some chords that intersect, and we're given some angle and arc measures. We're asked to find the angle TMU, which is this angle right here. Just call it angle 1. And it is congruent because it's vertical angles with angle WMV, which we were given an actual expression for. However, with the arcs that were given to us, arc WT and arc VU, it is, I do have a formula that I can use if I have an expression for one of these two angles. We'll call it this angle 2 and angle 3. These are congruent to each other, and we have a formula that says we add the two arcs and divide it by 2, it'll be equal to these angles, angles 2 and angle 3. So if I had an expression for angle 2, then I could set up an equation and solve for x. I'm only given this angle here, but I know that it is supplementary to angle 2. So that means 180 minus 3x plus 30 is how we can represent angle 2. So that's 180 minus 3x minus 30, or 150 minus 3x. So that's what I'm going to use to represent this angle, angle 2, 150 minus 3x degrees. So the formula says the measure of angle 2 is equal to 1/2 of arc WT plus arc VU. If I substitute all of those expressions and simplify, I can easily solve for x and then plug in, find my actual angle measure. Okay, to solve for x, I'm going to start by adding 3x to both sides. Okay. 150 equals 10.5x minus 7.5. So now I can add 7.5 to both sides. And when we divide by 10.5, we find that x equals 15. 3 times 15 plus 30, which is 75 degrees.